Okay, the last in our series of individual gas laws before we get to what we call the universal gas law, the combined gas law, is Gay-Lussac's law. And we've already looked at the two out of the three relationships. We've had P and T, V and T, and now this one is P and T. So there's a direct relationship between the temperature and the pressure of a gas. If one increases, so does the other, right? So you can see here, that the here's the relationship here is T increases, P increases, and vice versa. And you could basically write the similar relationship where P over T equals a constant, right? Because that's what that relationship shows. Because we could just as easily write the straight line equation, P equals K, which would be the slope, times T, right? So K times T, which is a constant. So other than that, there's really not much more that as there are with the other ones. It's a fairly straightforward two-variable relationship where you know one, you should be able to find the other. And then also you need to hold the volume constant, obviously. Otherwise, you don't have a relationship of P and T only. So again, we can write the more useful formula of P1 over T1 equals P2 over T2. And that's just as I said over here, P1 over T1 is going to equal the K, and the K is going to be equal no matter which P and T you have for this relationship. Again, I'm going to harp again, but the temperatures must be in Kelvin. Right, so I'll draw a couple more racetracks around here. And then the other thing too is that from the kinetic model theory of gases, we know that increasing the temperature gets the particles moving faster, causing an increase in the number of energy involvement in the collisions, which therefore leads to an increased pressure. We already know all that, so we've talked about that before, that kinetic energy is directly related to the pressure of a gas. So this doesn't, this just further enhances that statement more. So real simple, let's just going to do a couple of example problems, and I think you already know that this is fairly straightforward. So if you grasp the concept real quick, it's just a matter of a couple of quick things. So we're gonna say that a gas exerts a pressure of 1.2 atmospheres, and if the temperature is raised from a standard temperature to 89 degrees, find the new pressure. All right. So we know we need to understand that the standard temperature, if you remember, STP is equal to 0 degrees C. So 0 degrees C. That's 0 degrees C. And we know that because we're smart enough, we have to convert that to Kelvin, so that'll be 273 Kelvin, right? And which that is over here. And then everything else, we need to convert this to Kelvin. So 273 plus 89 is going to equal 362, I believe, 362 K. So we can put that into the equation. And our unknown is P2. And so we could solve for P2 using this equation here. We're going to rewrite it to P2 equals P1 T2 over T1. And then if we put in all the variables, we have 1.2 times, and then our T2 was 362, and then that's divided by 273. And so you should get an answer. So if you figure that answer out, then you're good to go. And I'm going to guess just right now that's going to be somewhere around 2 atmospheres. But let's see what it says on the next page. Okay, so I was a little off. It's not 2 atmospheres. It's actually 1.6 atmospheres. But that's the answer here. So we set it up the same way I told you to set it up. It's 1.2 over equals P over 362. And guys, I solved it for P that, and I just moved that over here to do the math real quick. And so that would be 362 times that, and so we would get rid of this. And so you should get P is 1.6 atmospheres. So fairly straightforward, nothing any different than what we've been doing before, except now we're just using P and T. So if a fixed volume of gas exerts a pressure of 1 atmosphere at temperature of 25 C, what is the pressure of the gas when it's heated to 100 degrees C? So again, we have a fixed volume. So every time you see fixed volume and then variables of P and T, you're going to think Gay-Lussac's law. And so we're always going to write the equation P1 over T1 equals P2 over T2. And we're solving here, so we have 1 atmosphere, and then what is the pressure of the gas when it's heated to 100 degrees C? So again, we're looking for P2, and so we should write everything out again, that P2 equals P1 times T2 over T1. And don't forget the T's here are going to have to be in K. So we have 25 degrees C, and we already know that T1 will equal 298, and then T2 will equal 373, right? And we already have an atmosphere for P1 was 1, so P1 equals 1. And if you should draw this out, we should get 1.25 atmospheres for our answer. So nothing more complicated than that. It's just a matter of just a couple of quick practice problems, and you should be fine on it. Just remember that if you have a fixed volume, you're thinking Gay-Lussac's law, right? And then fixed pressure and changing volume in T, that's Charles' law, and then Boyle's law as pressure and volume. So again, just another slide here to show you that the answer we did before was right, and this is the same way I set it up on the other slide, or rather just a few minutes ago. So nothing earth-shattering here. I just wanted to confirm that yes, indeed, what the way I set up was giving you the correct answer. Okay, so this is one of these end of unit or end of unit slides to kind of bring it all together, and says which will always decrease the volume of a sample of methane gas which occupies a volume of 2.4 liters at 25 C. And so there's variables here. So we're trying to figure out which is going to decrease the volume. So let's look at our several equations that we had with volume, and we had Boyle's law. So that's P and V, and that was a constant. So in that case, if you increase the pressure for increases, that would cause a decrease in volume. And then in Charles' law, we had V over T equals a constant. So in that case, if V decreases, then, if T increases, so let's erase that here. If T decreases, then V will also decrease. So there are two variables so far that if we know if P increases and T decreases, then both of those will result in the volume to decrease. So let's just look at the sample, or excuse me, a response here that has one or both of those in it. So an increase in pressure and an increase in temperature. So the increase in temperature is great, so that's a good check. But the increase in temperature, that's a bad, so that doesn't work. And then a decrease in pressure, well, that doesn't work because we've already talked about an increase in pressure. And a decrease in temperature, right? So an increase in temperature, or excuse me, a decrease in temperature. So decrease in temperature, so that's good, but this other one is out, right? And so then we have an increase in pressure and a decrease in temperature. Well, those both work. So there's an increase in pressure and an increase in temperature. And I already know that this is the right answer from the star here. But just for completeness, we have a decrease in pressure. Well, we know that's not going to work, so that's out. So no matter what it says in the rest of the thing here, we know D's not an answer. So D's out, B's out, A's out, and the only answer we have is C. Okay, so this kind of wraps everything up here, and we're talking about trying to explain something. And this is kind of what we did in the lab, although I said it was mostly for Charles' law. There was a reason why the can imploded as much as it did, and because several things. But not only did the volume increase because of the drop in temperature, but the pressure also decreased, which then caused the can to implode because the pressure on the outside had not changed. So let's look at that in a more close detail. The inside water vapor, so we had steam coming out that condenses, and the cooling causes a decrease in the number of gas particles and the pressure inside the can. The internal pressure is no longer able to resist the atmospheric pressure, causing a collapse. Right? Well, the decreasing the number of gas particles, remember, because the gas is condensing, right? We're going from gas to liquid, so the gas particles is decondensing. So therefore the amount of gas is decreasing, and therefore the gas number of particles, which then causes a decrease in pressure. A decrease in pressure also causes an increase in volume. A decrease in temperature also decreases the volume. So you've got two things that are happening here, right? So, and then the other thing, the external pressure in the can is greater than the internal pressure, and so it pushes on the can until finally the can collapses, and will continue to collapse until P inside equals P outside. And to do that, it's got to reduce its volume. Now we have what we call the combined gas law, and this is probably the most one of the most useful things that we have in science right now is the combined gas law. And the way it works is it's unusual to have a system with constant temperature, pressure, or volume. So by using all three of these laws together, we can make a combined law of Charles, Boyle's, and Gay-Lussac's, and then we can use that to solve conditions where all three variables change. So let's just look at it real quickly here. I'm going to do some circling here. So our first one here this is Boyle's law, so I'm just going to put B's for Boyle's, and then here's another one for Boyle's, and then we're going to use the red law for Charles. So red law is here for Charles, right? That's Charles, so that's C for Charles. And then the blue is going to be for Gay-Lussac. So the blue is just going to be on here, Gay-L, Gay-Lussac. So as you can see, all the variables are covered, right? And there we go. So that's now when we combine all these things, right? We get this thing called the combined gas law. Combined gas law. Right, I should actually make that a better color. So let me erase that so that you can actually see it when we put the video up. So the combined gas law, and it's the most universal, one of the most universal tools that a chemist has that can do for gas calculations, right? So this is going to be the combined gas law. So notice we only need, we have a bunch of variables that we can play with, and let's say we have P1, V1, and T1, or P1, V1, and then we're given P2 and T2. We can solve for V and T or something like that, no matter which one we have, as long as we have 4 out of the 5, all right, and we can get them to do that. So combined gas law. And one of the most useful things that we have going for us. Okay, so let's look at an example here where we can use the combined gas law, where a bunch of things are changing at once, right? So we have the pressure of a gas changes from let's just, before we get into this, let me just show you one more quick thing about the combined gas law to show you. So we know that P1, V1 equals a constant, and we know that V1 over T1 equals a constant, and we know that P over T equals a constant. So we have constant. So we have, when we combine all this, we know that P1, V1 over T1 each got to be also a constant, right? So it doesn't matter how we set it up with all these, it's still going to be a constant. P1, V1 over T1 is going to be constant. So if you then you could equate that to a P2, V2 over T2 was going to be that same constant. So we now can change a bunch of different things at once and not have to worry about, well, I can only hold one constant and I can't hold the other one constant. So anyway, I just wanted to put that in there real quick to make sure that everybody was understanding of that. And so let's just look at our thing here. So we have 6 out of the 5 variables that we, or 5 out of the 6 variables that we need. And so here's our equation. We have the gas pressure changes from 120 kPa to 50 kPa. So we have a delta of that. So that's the delta P there. And then the volume changes from 4.5 liters to 40 liters. And then we have a delta V there. And then we have the initial temperature of 81. What was the final temperature? So we have to have a delta T that we're looking for. So all these things can combine together. And if we just do the math here, or do the thing here, we have 120, I'm not going to worry about the units yet, times 45 divided by 354, and that has to equal 50 times 40 divided by some type of t, right? And so you could solve all that, and then you should come up with a number that's quite small actually for t, because it has to be, the ratio here has to be the same as this one. So let's look at that, see what that is on the next page. Okay, so we haven't had the answer yet here. So let's just do the math real quick. So 120 times 45, well, that's going to be, what is that going to be? About 4,500 plus 90, so that'll be 5,400, and divided by 354, and then that's going to be equal to 2,000 divided by T2, right? And then, so that's roughly, 5,400 is roughly 2.7 times this. So this is going to be 2.7 less than that. So T2 should equal somewhere in the order of like 118 degrees Kelvin, if my math's right. Maybe not exactly that. If I could do the math, I guess, real quick on my calculator to do that. I'm just trying to get the thing here. Let's see if we can do this real quick. So anyway, it's just, the bottom line is, so let's just do this up here real quick. 5,400 divided by 354 equals, and then that's 15.2. Let's do this a different way. So 2,000 times 354 equals divided by 5,400 equals 131. So 131 Kelvin it should be. All right, so let's just erase that. 131 Kelvin, which is quite small, 131 Kelvin. And that's to do a double check here, so let's just double check it just to make sure. So here we go, 2,000 divided by 131 Kelvin equals 15.2, and then we have, all right, so that's the correct number. What's 131 Kelvin? And then we need to subtract that from degree C, so we know that Kelvin equals 273 plus degree C, and so 131 minus 273 equals, we have a minus 142 degrees Celsius. So quite cold, right? We started out at 81 degrees C, and now we've reduced this to 142 degrees C. So it's quite cold. So anyway, so that's how we set that problem up. So hopefully that was useful and helpful to you. So let's look at the next slide. So here we have a new one that has the gas is occupying a volume of 34.2 millimeters at 15 degrees C and a pressure of 800 torrs. So just a little bit more above than 1 atmosphere and a little bit colder than room temperature. What would be the conditions and volume of this gas at standard conditions. And so we have to remember the standard STP equals 0 degrees C, or 273 K, and 1 atmosphere. So my guess it's going to be fairly close when we do all the math, because we're not really changing that much here. This is a little bit colder than the room temperature, and this is a little bit, and the new pressure, the standard conditions are a little bit, the pressure is a little bit weaker than 800 torr. Well, we got to do the math, and so when we do all the math here, we got, as I predicted, pretty close to where we would start it from, right? Because these two are close together, and these two are close together, and so these two should be somewhat close together. Just as a mental check, right? But then we do all the math down here, and we get the proper number, which is right here. So it's a good thing to always go back and do a mental check to make sure your answer makes sense, right? So this answer is here, and it does make sense, because 800 torr and 760 torr, there's not much difference there. Yeah, there's 40 torr, but it's about it's less than 20%, less than 15% or something like that. It's 40 over 80, right? So which is 4 over. It's 40 over 800, which is 4 over 80, which is about a little about 6%, and then the other ones too are roughly the same way. So it's not that significant of a difference. And again, here's our last one here. Gas occupies a volume of 444 milliliters at 273 K and 79 kilopascals. What is the final temperature when the volume of the gas is changed to 1800 milliliters and the pressure is changed to 38 kilopascals? So we can, you can do all the math. Let's just do P1, V1. Just put all the variables in so we know Vn equals P2, V2 over T2, right? And 400 starts at this volume here, so this is our V1, so I'll put that there, and here's our T1, so that goes there, and then our P1 goes here, and then our new ones go, let's do this different color for that one. Let's do a different color for that, just so we make sure that that's good there. So we'll put that line back in, right? And then we'll do a different color. So here's our new one, and that'll go here, and then this one will go. Actually, this will go here, and this one here, we'll make that go over here, and we're looking for this answer here. This is what we don't know yet, right? So let's just do the quick calculation here. Okay, so we have everything's in K, so we don't have to worry about that anymore. So let's do it's 44 times 79 divided by 273 equals, so that's that number, and then we need to multiply that number by P2, which is 38.7, and then we need to multiply, actually we don't have to do that at all. We have to, let's redo that again. Let's just set this up so I can solve it easily with a calculator. So T2 is going to equal P2 V2 T1 over P1 V1. So let's just do that real quick. So we know P2 is 38.7, and then we know that V2 is 1880. All right, so that's that, and then we need, guys, T1, so that's 273, and that equals some large number, and then divided by first volume, which was 444, and the first temperature, which is first pressure, which is 79. And you should get 566 Kelvin, right? So that should be your answer, which is pretty hot. Right, so that's good to go. So as long as you can follow how we do that, then you should be pretty set. And again, this is just the way I set it up on the other page, but here just tells you that, you know, again, here's our t that we're trying to solve. We solve all this, and you could just basically put this here, and then this part goes here, and this one goes here, you know, times that whatever this stuff is, and then you're good to go, and then you should get the same answer. I mean, if you need to do math a different way, that's fine, but this is the way I learned how to do it. So the crisscross. And again, just more practice here. So the temperature of a 2-liter sample of gas at STP is increased to 27. So we start our new conditions are P1 is 1 atmosphere, because we already said STP, and V1 is 2 times 2.0 liters, and then 273, and then it has to equal our new thing here, which is temperature is increased to 227, so that'll be 300 degrees, 300 K, this is K, and then that's going to be over a decreased pressure, so that's going to be 80 kPa, but 80 kPa is actually, we have to do the conversion there because we're not given conversion here. Or I guess we could go back to here and put this value here. I always like to work in atmospheres, but you don't have to. I guess we could do this value here in the kPa to make everything easier. So let's just put that in there. So that's 101.3. There's a point there, 3 kPa, and times 2. And then we have 80 kPa, so we don't have to do any more conversions. And then then we have to find out what our new volume is, so that'll be times V2. And so you can just do that math real quick, and you should get an answer that you know, it's going to be somewhere around 2.8 liters, I believe it is. Let's just try it out here. So it's got 101.3 times 2 divided by 273 equals, so that's that number, and then that has to get multiplied by 300 equals, and then divided by 80K, 80, and that should equal 2.7 liters. So that's close enough to 2.8 liters. 2.78 actually. So there you have it. Nothing more challenging than that. It's just a matter of just keeping track of where all your stuff is and making sure that when you put it in the equation, you have the right variables for each variable in there. So if the right P, the right value for V, and also make sure you have your temperatures in K. And again, it just confirms what we just said. So here's our equation that I put together on the other slide to show you how I did it, and then you get the same answer. So our last thing for this, and this is only a one slide on Avogadro's law, and remember back when we talked about STP back in earlier along about moles and all that, that 1 mole of gas, I'm going to just write it here, one mole was equal to 22.4 liters of gas at STP, and this is exactly what it says here. And it says that equal volumes of gas will contain the same number of particles at STP of any given gas, right? So 1 mole of gas equals 22.4 liters. Therefore, 1 liter of gas will have the same relative number of particles as another liter of gas, right? No matter what the gas is, right? Because if 22.4 liters has the same number of particles, and which is Avogadro's number here. Then if I just divide it by 2, then it's just half that, and then everybody gets half that too. So if we divide this by 2, we get 11.4. And 11.4 liters has just half the number of particles. The ratio is the same, right? No matter what the ratio is. I mean, the ratio is the same as long as I divide 22.4 liters by this for all the gases, right? So 1 liter of H2 gas, 1 liter of this, will equal 1 liter of this as far as the number of particles, which equal to 1 liter of this. It just as 22.4 liters would, and 22.4 liters would, so would 1 liter, right? Because they're all STP, and we all know that the number of particles won't change. Obviously, the gas mass of that gas will change because each gas has a different molar mass. As you can see here, each one is a little bit different molar mass, but the number of particles per volume won't change. And that's all that Avogadro's law says, that equal volumes of a gas will contain the same number of particles. And that's pretty much it.